K or S over here reversibly, so there's an equilibrium, and then the bound form over here the protein can be degraded and releases a free unit of the degradation complex. Yeah? So there's equilibrium here between the degradation complex can bind and unbind the proteins, then the bound form can have the protein being degraded. Okay. Yes?
For G1, what does it mean for an unbound protein to be unbound plus
Sorry, what?
G1, second one.
So this is the unbound promoter, right? And it has a synthesis rate of the protein, right? So when a synthesis happens, you have the reaction of this unbound promoter is still being there.
It's a very small synthesis rate, yes.
Yeah.
This is what we call the basal rate. You always can produce, but it's very unlikely.
Okay.
So you have like when it's bound, you have a big synthesis rate. When it's unbound, you have a very
small.
small.
This is a small rate. This is a big rate. Yeah. Okay. So we're gonna use the stuff that we talked about yesterday in the system now. We're gonna first write down the deterministic kind of equations and plot those nullclines and see what kind of fixed points do we get, and we're gonna see what kind of parameters are useful, and then later on we're gonna see the noise, what role noise plays in the system with the stochastic method. So these are the deterministic equations. Here's S, where you have this Hill function over here modulating the synthesis rate. And this is the Hill coefficient over there. In the original studies that people do with this, they use a very high one over here because that fits back. That's what we were talking about yesterday. So this is synthesis. This is the synthesis of K. That's the same idea. You're averaging the two synthesis rates, the bound and unbound synthesis rate, according to the concentration of K. Considering that the binding and unbinding happens really fast. Then over here, this is the same for both cases. This is the degradation, where there's phi here that depends on the concentration of K and S is the availability of the degradation complex. This goes from 0 to 1. And this is the maximum degradation rate. That's the degradation rate that you would get if all of the degradation complex was free. Okay, so and this function over here, we can deduce that from the equations, the chemical reactions that we defined in the previous slide. Okay, so now we got those equations and plot this nullclines, right? The nullclines are the curves. You get the deterministic equations and you set the derivatives to 0, and you get these curves, right? So the red curve is the curve where the dk dt is 0. The green curve.
But just remember, by the time you set derivative equals 0, you're going to get a stable point, unstable point, or a settle point.
And
right?
where they intersect, those are the points where both dk dt and ds dt are 0. And that's a fixed point. And they can be stable, unstable, or a saddle point, right? So you get this kind of curve. And these are 3 of the different, and these are for different parameters. Right? So depending on the parameters you use, you can get stuff like this. Sometimes you get just one stable fixed point. And in this case, the system is going to stay here forever. Sometimes you're going to get, what you have here is like one stable point here, and there's a saddle point, and another stable point here. Then you're going to get two stable solutions. And what the system is going to do is spend time in one or the other, and depending on noise, maybe switch from one to the other every once in a while. Or you can get something like this, where you get a stable point here, a saddle point here, and an unstable point over here. So this unstable point is not really stable. This thing goes around there, but it doesn't stay there. So it would be here most of the time, but every once in a while it would like to come to the vicinity of this point over here, but it wouldn't actually stay here because this point's not stable. It would go back to this side. And this is interesting because that's actually how competence happens. Right? It's a cycle. The cell goes into competence for a while and then comes back. So you would have this kind of situation over here if you plot the surfaces over here. These are surfaces plotted over the nullclines plot that we saw in the previous slide. These are obtained by simulation, where you get stochastic simulations, and then you get all the probability distributions of having all the numbers of com k and com s, and then you get the probability distribution, and you do minus log of probability distribution is something that it's an effective potential, not a real potential, but it's an effective potential. It just gives just a relation to energy landscapes.
Not just because they brought yesterday. We are calling that an effective potential because put minus log of probability. But remember, you don't have microscopic reversibility here. Loss is guaranteed. So you're getting this probability out of the system that doesn't satisfy thermodynamics, right?
Yeah.
So you're plotting something that's like a potential line, but you know it's not a real potential because the equations
Well, you got
are not
something,
satisfied.
well, you got something that resembles energy landscape. That's good to visualize. Okay, so you see over here in the yes.
What's the probability again?
So
Probability is the probability of what?
the probability of having K proteins and S proteins. Yeah. Okay. All right. So see this is where we have only one stable fixed point. You can see that you only have one well here, and you never get out of here. You just stay around this point. Here's where you have two stable points. You can see there's a well here, another well there. So it stays here most of the time, and sometimes it switches over there and it stays there a little while, and then switches back over here. And this is what we call this is a bistable, yeah? And then this is what we call the excitable. It's the one that has a stable fixed point over here and an unstable over here. So you can see that we don't actually have a well here, but you're not concentrated on the point over here. Even the system actually does go here, comes here and back. It never really stays here, so you don't have a well forming over there. Okay, so now.
I'll just remind that of the excitable. An excitable system, you have a system that's mostly on the stable point. Sometimes noise kicks in and hit you up there, right? And then you go in a well and finally the cycle, right? So that's
Yeah. Okay. Okay. So somebody asked me yesterday, I think, what do we do with the rates? What do we do? How do we get the parameters for this kind of stuff? And this is actually what we did in this case. You don't. It's really hard to get these rates from literature and biology. They're really easy. They're really hard to get. And
all of
they're not
them.
very. They're not very. Huh?
Some of then you can get persistent.
Yeah, they're not very reliable, and this is hard. So this is what we did. We generated 500,000 random sets of A-dimensional. We scaled all the parameters, and then we generated 500,000 random sets of parameters, and then we analyzed all these sets to see what kind of distribution of fixed points we would get. And then we divided them according to how many fixed points and what kind of fixed points they had. And these are the plots over here of the average set of parameters for every configuration of fixed points that we got. So you can see a bunch of them didn't have any fixed points, and then you got like up to 5 fixed points for some cases over here. And then you have like 1, 2, stable, unstable. There's one with just one unstable that the system never settles down anywhere and just like moves around all the time. And then we just got all the random all of the sets of parameters that got that showed the one stable, one unstable fixed points over here. And so we got all those sets of parameters that showed that kind of behavior. And here's a histogram of what kind of parameters show that kind of excitable behavior that we're interested in. You can see that these are a pretty nice broad distribution, so that indicates that that's like a compact region of the parameter space that shows that kind of behavior. So what we did is we took the peak value of these distributions to use as our standard parameter set here. Okay. So now we're going to use the stochastic methods to see how noise interferes with this system. So now we're going to get all of these reactions over here that we have and consider them stochastic events. Then we're going to use the Gillespie algorithm, the simulation that we talked about yesterday to simulate it. And then we're going to see where the noise comes from and what can we do. And maybe compare it to what you get in the papers that the biologists did. First, we're going to see how if noise coming from the degradation complex plays any important role over here. That would mean, what I mean by noise in the degradation complex, it's basically how fast this equilibrium is over here. If so, here's the adiabaticity parameter for the degradation complex dynamics. So if you have a high omega d here, that means that this equilibrium happens really fast. If you have a low one, it means that this equilibrium happens slowly and there's noise coming from there. So then we simulated for a bunch of different parameters, and what we got is actually
Sure, discuss that. I think you said, but let's repeat one more time to understand. If you have the degradation as a very slow process, then sort of the degradation events are happening on the same time as the entire event of the process. Then fluctuations become important, because we may have 2 or 3, and that's a big difference. But if the degradation is very fast compared to the overall time, then fluctuations are small, and you can treat it in a deterministic way. That's the case when noise is not important. So you get noise from time scale here. So by the time you put discrete events, you can always get noise from time scale. If you have very few events, then you know the fluctuation is important. So that's why you always do this time scale approximation, the best way to figure out if you're in this regime where fluctuation would be important or not.
Yeah, so the energy landscape is kind of very similar. And these are the intervals of the competence cycles, like how long they last. And this is the probability that you're going to have a competence cycle, and it didn't really alter any of that. So we concluded that the noise coming from the degradation doesn't really play that big of a role. And what you can do then is just average out all of this reactors over here, and then just put one K and S dependent degradation rate for both K and S. So we don't really consider them explicitly from now on. Then, now, if instead you vary the omega, that's the same omega that we were talking about a lot yesterday. The one that measures how fast the binding and unbinding to the DNA is compared to the other time scales of the system. Then you see some differences. So here's the same energy landscapes and the same effective potentials. For this is when it happens when the binding is really fast until it slows down. This is when it happens really slow. And this other plot is a sample of a trajectory. And blue means the gene is unbound, and red means the gene is bound, and you have a high synthesis rate of concave that's going to throw you into a competence cycle. Okay? So over here, of course, all blue because this is the average out over here, so there's no bound and unbound there. So here you see that it binds and unbinds still pretty quick, right? And you see the cycles over here. It goes around, like the unstable point is around here, right? And the noise will throw the trajectory around the unstable point and back to the vegetation well over here. So, yeah, this well over here corresponds to the vegetated state, right? Low, concave. And this cycle over here is like it's high concave, so it's this cycle over here that corresponds to the concave. And then you see if you make this the binding and unbinding really slow, and you see they have a binding event that will throw up here, then an unbinding event that's going to throw it back down there. And you see that for lower values of this adiabaticity, the reason where the unstable point is over here, you see that the system never goes there, and it has a really nice trajectory around that point. See over here. So binding event over here, then it goes around over here, I do have an unbinding event, and it goes back down there. And if you see this trajectory through time, you see this peaks in concave that
so what's the green and the red?
So the red is the concentration of concave, and the green is the concentration of comass. And the peaks in the expression of concave would correspond to competence behavior, right? And again, for the same idea, binding and binding really fast, binding and binding slow. And fast and really slow. And here you see that when you have a slower binding and binding, you have this really sharp transition. You have a binding event and the proton level goes up really quick and stays there for a while until it comes down really quick. And you see that the time that you spend in competence is higher. You can see already from here for this lower values of omega. Now, this is the same idea as yesterday. This is a movie with little worms jumping. And here you have, on top, you have the unbound DNA, and on the bottom you have the bound DNA. So this over here is for slower binding and binding. So you see that then we're going to jump down and then go to competence, and then we're going to jump out and then come back from competence. See, it hangs up there, it's unbound, and then at a certain point, it's right around now again. Yeah. It goes to competence and comes back. Yeah. The combining event will take all the way to competence almost, and then come back. Then you can have the same idea for faster binding and unbinding. That's what you see. That's what we're going to see in the bottom, where along the cycle you're going to have lots of binding and binding events, and you're going to see the system jumping up and down a lot more than you see in the top. See, it jumps up and down a lot, but that means it's binding and binding more. And binding event not necessarily will take it to competence, but every once in a while it will. You'll see it go there. Okay. That's the one. Okay. Then, now, this is just a plot of looking at the adiabaticity parameters. How does it influence the probability that your system is going to go into competence, and how does it affect the time that it spends in competence? You can see that this is normalized to the time, to the values of omega infinite. That's like super fast binding and binding rate. So for smaller values of omega, you have the competence time growing, and also the probability of initiation also grows. And it comes back down, and it's really small, slower than 1. So this means is even for still pretty high values of the adiabaticity parameters, even when the binding and binding is like still as big as 10 times larger than the other time scales, you still have pretty important effects over here. You can have regions of the parameter space that can show competence, even if the binding and binding is not that slow. Here there's already some comparison to stuff that people did in biology. This is the graph that people have that taken from this one of the papers. This is an experimental graph that's measuring the probability of having a competence cycle, right, as a function of the basal level of production of those two proteins. And how do they do this in biology? You can put plasmids, which are little pieces of DNA, coding for whatever you want to express, and you can put whatever promoter you want there and whatever protein you want to express with that promoter, and you put that inside the bacteria, and the bacteria is going to express over there. So if they put plasmids with the conK gene, you can have a higher rate of basal expression of conK. Same thing with CoMS. And the problem, if you have a higher basal level of expression of K, you increase the probability that you're going to have competence cycles. And that doesn't happen with CoMS. You have only this slight increase over here that we're going to talk about a little bit. But, the paper they claim it doesn't affect at all, but you do see a little increase over here. What the basal level of CoMS does, I don't have it here, but it's in the biology paper too. This increased level of basal expression of CoMS is going to give you longer cycles. And a larger basal expression of K will not affect the length of the cycle. And here is what we get from the simulations, right? This is a higher basal expression of K. This over here is the same plot as this red line over here. And you can see that you have the same kind of increase. And you see that the higher basal expression of K doesn't affect the length of the cycles. Okay? So this corresponds to what you see about. Then this is higher basal expression of CoMS. And you see that it does increase the competence times. And here, and this is the interesting one, is the probability that you're going to have a competence cycle, or by the basal expression of CoMS. And you see that over here, the noise coming from binding and unbinding plays a big role, right? This red one over here is really fast binding and unbinding. And you can see that this really doesn't change the probability of competence cycles. The blue one over here is for really slow binding and unbinding. And you see that you have a way larger probability of competence cycles. And here, this green one is for when binding and unbinding is only 10 times faster than the other time scale. And you see a slight increase over here, which is something that you do see in the biology experiments, right? There's an increase in the probability here for larger values of basal expression of CoMS. Here are the pictures of those experiments. This IPTG here is an inducer they use for the promoter and the plasmid. That's how you can tweak the expression rate.
Now, so now you're going to do the full comparison using omega equals 10, right? This comparison is made for omega equals 10.
Yeah, well, yeah.
Based on the last plot, right?
Yeah. Okay. This is what happens to the colony of the bacteria when you increase the basal expression of K over here, right? You remember that when you increase over here, you increase the probability that you're going to have competence cycles. So here you have competence cycle every once in a while, and then if you increase it more and more, then you end up having lots of competence cycles, and the system kind of oscillates. And if you go back to this kind of parameters for the nullclines plot, this is the situation that you have when you lose that stable fixed point, and you end up with only the unstable fixed point, and then the system never stops. It just goes around the unstable point, and that's why you see this constant oscillation over here. And then if you go even further, you end up with just having everybody just going into competence and staying there. These are the simulations, and you can see that we get the same kind of behavior here. It would correspond to something like this. Huh? If it's time? Yeah. Yeah, exactly the same in all cases over here. There's the same kind of plot for the red here is the same kind of plot as the red here. So yeah.
How do you calibrate your time using the cell cycling time?
Yeah, because since we're using scale parameters, if we want to plot the same kind of, if we want to compare our simulation plots to the experimental plots, we have to define our time, and we do that based on the. We take a length of a competence cycle in our case, in our standard case, and we say that that's the same as the length of a competence cycle in the experimental case, and then we calculate our time according to the doubling time of the lifetime of the cell. So that's how we get our time over here.
Sorry.
Yes.
So you're saying that there needs to be a check this time. So based on the residence time from your probability graphs of how it will go from one stable state to another one, which is the confidence state. That's how you calculate the confidence time?
So we have all our scale parameters, right? So we don't really have like rates. And we need just like one reference to get our rates, right? So there is a competence cycle and experimentally less like I think like 20 hours. Then we get like with our standard set of parameters that we're going to base on everything. How long does the competence cycle last over there? Whatever. Then we just say that that's the same as the experimental one. Yeah.
So how does that compare to the trajectory plots that we showed you?
How does that compare to the trajectory? We didn't use time until now. Yeah. So.
I was at some point you have to get your calculations that you from your model to match up with the experimental, and that's part of what you're saying. But if you did an experience,
Yeah, we got our standard competence time, and we say that's 20 hours because that's what we got. Well, yeah, and then the probability we calculate with the way they calculate this probability in biology is the probability that you have that you're going to have a competence cycle in the lifetime of a cell. So then
But that's an interesting question in the following regard. When you do a model like that, a lot of these rates are not known. So you create your model, you investigate the system, you get a set of parameters that you believe that give the behavior you want. Then you get all these sort of fake times of simulation. Now you have to relate fake times of simulation to some real time. You end up with two possibilities. You can get a standard competence time, or you can get the time of cell division. You play with the ratio of those, and then you calibrate them. Now, you're entitled to say, is that a good approach based on calibration? So the next step in all these things with theory is basically, now by the time you do set your time, you can compute all your rates and everything. So now you can go back and start to check if these rates for degradation, the rate for binding and all these things, they are related to molecular biology. So it is, like I said, a self-consistent cycle. This is sort of a first time if I do that. That's why you cannot have all the answers, but they're absolutely correct. It'd be very interesting if now you do these things, everything appears to be okay, but then when you compute your binding time to the DNA, you get a time that's totally ridiculous in terms of what you think is physically feasible. Then you have to step back and work around.
Okay, so this is what we get for increasing the basal expression of command. You see that initially here the probability of having competence cycles doesn't really increase that much, but you see that the peaks here are wider. That means that the cycles are longer. Yeah, and then but in our simulations here for moderate value of the speed of the binding, you see that you do get more competence cycles at the end here. And it's really a shame that they only put one peak in the experimental paper, because we'd like to see if they get that increase.
Well, they get broader, but
They got broader. They're putting blank lines after it, so we can't know for sure what they found. Okay, so these are some other plots of this is here is you're increasing the basal expression of K and S, and here you're going from really fast binding to slower, and let's see what it does. Here you see that as you go to slower binding, you see that this region of this counter curves are the same energy transcripts over there. And you see that for slower binding, you get these regions here being more populated, right? That corresponds to having more cycles. And when you increase the basal level of MS here, if you make your binding slower, you see that you start populating more this high MS areas over here, and that's where you start the cycles, right? So that's why you get some more cycles over here. And if you see the axis of this figure, you see that this is way longer, right? So when the cycles go around here, that's a larger excursion. That's why the competence times increase from higher basal expression of competence. Now some more movies, and I apologize for the low quality of this movie. Well, not exactly Spielberg or anything. This is what we get for the standard set of parameters that we use. So this is what we're going to be comparing the other movies to. So it hangs around the middle there for a while, and every once in a while it goes into this excursions around the stable point, and then comes back there. But it usually stays in the excursions have a different mass there. Okay. Now, in the second one, the second one, is for a higher rate of expression of basal rate of expression of concave. And after the movie star, it kind of stops going very well. You notice that you have lots of cycles. The system keeps going around, it keeps going into competence cycles all the time. That corresponds to the higher probability of the competence cycle there. And in the third one, we'll just finish. In the third one, see that it doesn't go into this competence cycles as often. It hangs on vegetation more than in the previous case, but the cycles are longer, and they have a longer excursion, so they take longer. That's why the competence times are, you see that increase in the competence time for the higher basal expression of comments. I think I should be done over here. So I'm just gonna skip this part. each one of those cells are independent stochastic simulations, and where the level of concave is the color axis there. So it's yeah, it's funny.
Are we getting the right 10%, 5% here?
Yeah.
What are the motions we are seeing?
Sorry?
What are the motions we are doing?
Blanks.
Yeah.
Oh, it's in that lab. I don't know of any better because I can only do this in 3D and then can do it in the top view. That's the only way I know how to do this.
No, but this is not this.
That's fine, because this is a 3D view from the top that I can do this movies for. Alright. Okay.
But before you finish, I want to make a comment that was interesting from yesterday and today for people just to notice, is a lot of discussion into this gene switch. People were talking about having sort of a real switch. What we're seeing a lot in biology, and we have more examples, there are problems of HIV virus with someone in San Diego, that actually a lot of this biological control appears to be more efficient, not as a gene switch, has excitable systems. We stay on a stable state. The initiation process depends on some random event. That's the concave. So that's why we call the initiation event is random. But after you do that initiation, then you go into this transitory state that's a limited orbit with a fixed time. So you have random events that you start, but then after you get into there, you have a fixed time orbit. And it appears to be more the case in many of the biological systems, where you want to have something to give an order to start, and then you just want some time to take care of business and then go back where you were, instead of being a pure switch, where you have a random event to go one way, and then another random event to come back. Here you have like a random event to go in, then you go on a limited orbit, and you go back. Questions?
Questions?
Yeah. So, many years ago, Prigogine, looked to these cellular events. Yeah, Prigogine, he looked to these cell events and other people, of course, but not prior for the growth thermodynamics. And he used to treat, not, of course, he didn't have the tools, but he would talk a lot about the flow of entropy, calculate look exactly to this oscillatory reaction. So do you think you can extract, this reversible thermodynamic
That's always a
parameters?
good question, right? Basically, Prigogine was very courageous. We are not that courageous. We are on the step that we are courageous enough to plot a PMF. Okay? By the time I have a funny PMF, I can have a funny entropy and a funny enthalpy. We can all, right? The question is, what's the meaning of these things? And actually, there is a way of ascribing flows on equilibrium systems to entropies and things like that. If you're going to be able to go to a very far from equilibrium statistical mechanics, and you'll be able to ascribe flow to something that's entropy-like. I think that's an interesting question mathematically. But it's a dangerous field, right? The interface between real size and fleetness becomes smashed very fast, so you have to be careful, but that's a good question.
So, considering competence, the cells uptake DNA from other bacteria.
Any kind of DNA.
So, is there any chance that they uptake more competence or concave DNA that would influence the cycle like the long or short?
I guess, but I don't know. And they do take whole pieces of DNA. So I guess there is a possibility that they will take a piece of DNA that has this gene promoted,
But just wet.
That would be unlikely.
What do we take DNA? when you uptake DNA from the other cells or take everything from the other cell, you then and eat them. By the time you become your own to survive, there's interesting thing. The easiest answer is to claim, okay, you're taking this DNA and you're just digesting it and it's just food. But then you could also maybe you're trying to look for some particular species that has some genes that may help you to live by fluctuation on some difficult environment. But we are far from knowing these things, right? So disease-based feeding is a good reason. Based by that, then you can duplicate and try again. Or you can just save yourself enough food before you sporulate. I don't know, but I don't know the answer. But that you could do everything else, but I don't think that people know this. They know what's the further downstream network that comes after competence.
Precisely what the function of competence is still, there's a lot of, we're still talking about it. It can serve many, many purposes. Yes.
If you can go back to the very first slide where you represented the concave, convex side and the different binary bonding situations.
Where?
It was the very first slide that you showed that. Go back.
There?
Yes. I wanted to know, so the different times when the concave starts to show up, how significant is it to look at when that timing starts? Because for the first three, where you have large omegas, it starts just about 40, but for 0.1, it starts slightly below.
No, this is just a 100-second window of time that contains a peak. I guess the only information you could get this in over here is that in none of this case you get more than a peak in 100 seconds.
No, but the next slide, go to the next slide. So this is just an example. The one where you show the initiation times and the things that show the slope. That's the one that counts.
Which one?
On this slide where you show the distribution of initiation time versus no, the one you compare to experiments better. Here, right? Then here's the one that counts. You have to do the initiation time and see how that varies compared to experiment. That's to tell you how long it takes before the peak comes, right? That's what initiation time is.
Probability of initiation, the probability that you're going to have a competence event in the lifetime of a cell.
And actually, just one more clarification. I know, I remember from yesterday that you defined a parameter for the adiabaticity. Is that related? Because I saw here you represent T over TC. Can you remember?
Oh, no. The TC is the competence time, it's like how long a competence cycle is. And this PI is the probability that you're going to have a competence cycle within a lifetime of a cell. That adiabaticity parameter omega, like that we use here, is the same one from yesterday. That's unbinding rate over degradation rate. It just measures the speed of binding and binding.
Okay, we better go to Jerson, right?
Okay.
Okay, let's start. I don't want to delay the excursion, so it's taking 1 hour. I might talk about 45 to 50 minutes, so we can have some questions. So yesterday, I pretty much focused on small system. Today, I think it will be very easy to go now to the second part of my lecture. I'm going to talk about aggregation, and Daniel Cox has done a superb job in presenting a lot of the literature and a lot of the questions that related to these protein folding disorders, in most of the cases forming amyloids, but also there are some other disorders that, for example, it's not clear if there is an aggregate, so you have protein going from misfolded conformation, eventually leading to diseases, sometimes like cancer and another disease. So, in many cases, of course, you have formation of aggregation, so eventually, not for all the case, but you have intermediates that are stabilized in this folding landscape. And of course, once you have aggregation, and if it becomes irreversible, it goes all the way down to the it's like a sink, and at some point it's reversible, but at some point it becomes irreversible. And when, of course, when you start to make very long and large amyloid fibers, in the case that you make amyloid fibers, then it's very unlikely that you can go back. And there are other forms of aggregations. For example, there's some other, I'll comment a little bit later on. The beta coil, phase spike protein, when produced in bacteria, it goes to inclusion bodies, and that's quite a good model to study how to dissolve these aggregates. For example, if you want a protein with some medical application, pharmacological application, if you are expressing in some heterologous system, sometimes it's quite a big problem to recover the protein that you want active and is there in those inclusion bodies. So it's also it's quite interesting to try to find ways to dissolve those aggregates too. So most of my talk, I'll be focused on this on the proteins involved in these three diseases: alpha-synuclein involved in Parkinson's disease, the tumor suppressor protein p53 that is involved in cancer, and the prion protein. So, as I mentioned, once the protein goes to a misfolded conformation, and if you don't have back the right structure, you may have two outcomes. So it can either be degraded, so you may have the misfolded or the protein conformation disease because you don't have any more the protein, so it's a loss of function. The cause of the pathophysiology of the disease is the loss of function. Or you may have the other way around, like in Alzheimer's disease, Parkinson's disease, prion disease, you have a toxic gain of function, either of some oligomers or because of the amyloid. And it's the real scenario, probably you have both of them. So the sum of the proteins, since we don't know, for example, the function of the prion protein, we try to believe that this is the predominant cause of the disease, but we don't know for sure. There are knockout mice without prion protein, but there are no knockout people with prion protein. We don't know if prion is involved in some important functions at some, especially some tissues, especially at the neurological in the brain. So, looking now, I mean, of course, as a biochemist or biophysicist, we try to isolate and try to understand, I mean, not only what's caused the disease, I mean, but how we eventually can reverse this disease by, for example, by finding some compounds that will prevent the formation of the oligomers or formation of the amyloid fibers. So at the end, you don't want to have these. You don't have to have the brain full of plaques that are extracellular plaques that are destroying the brain cells and then with the lack of function. So on the other hand, there is a now physical chemistry approach to try to, and remembering about what we discussed yesterday about when protein fold, they of course several things occur, but one of them is really to get dehydrated. So you have the hydrophobic force that predominates, and then you have the final conformation with much less hydrated than the unfolded conformation. And in this respect, I mean, formation of amyloid fibrils or other aggregates, in most of the case, you have also dehydration. So you have the way to, there is this very subtle balance between going this direction and going this direction. And I think also Daniel Cox pointed out that, like, it was stopped by Dobson saying that maybe most of the proteins, or all the proteins, will have in the phase space conformation as an amyloid. So, especially because it gets quite stable once you go all the way to the aggregation. So yesterday, I pointed out that maybe one way to study all these reactions would be to use, in addition to all the tools that people have used, also to use the pressure X, in addition to temperature, chemical perturbation, and so forth. So, and particularly, pressure is interesting because one can populate, I mean, although this diagram that was people have done for different small monomeric proteins. I mean, the protein once gets out here, sometimes it's still partially folded, and if you denature by temperature, you go slightly different state. And the reason for that is that when you use high pressure, you are affecting predominantly the hydrophobic interaction. You are shifting the equilibrium towards smaller volumes, you are releasing those calyx, you are hydrating this hydrophobic surface, or polar surface. And on the other hand, I mean, for example, if you have like this denaturation reaction, if you have here, for example, just a small alpha helical peptide, let's say, 20 amino acid residues, if you apply pressure, nothing will happen. You can go to 10,000 atmosphere because you're not going to affect hydrogen bonds with pressure in this pressure range. I mean, remember that up to 20 kilobars, you don't affect bond lengths and bond angles with pressure. That's a lot of pressure, but it does not affect. And also, you don't affect hydrogen bonds because once the hydrogen bond is broken with when let's say a helical protein or a beta sheet, I mean, it's replaced by hydrogen bonds with water. So I mean, there's the volume change is very small for this exchange of hydrogen bonds, protein, hydrogen bond, and protein-water hydrogen bonds. So that's the main reason. So of course, it's like someone mentioned yesterday, it will depend a lot on the phase, in particular phase diagram of the protein you are studying. But we and other people, so pass this slide, that have seen that there is this very nice paper by Akazaka, published in PNAS he asked that when he has lysozyme that is a conformation that is justified deficient, it tends to go to the amyloid conformation. And then if you apply pressure, so you all up over here, if you apply pressure, you dissociate the aggregates. We have seen in several other cases, for example, for, let's say, for inclusion bodies here, and some proteins that are expressed also by people in Colorado, Carpenter and Randolph in Colorado. We have a patent. We're disputing this patent because they patented in Europe, we patented in the US. But we published first in 1999. They published 2 months later. But anyway, the main thing is that one can use high pressure. In some cases, unfortunately, none of us is going to get too much money because it doesn't work for some proteins. One can just dissolve those inclusion bodies with high pressure. And in fact, they have a small company that are doing that in direct pharmaceutical companies. Also, I mean, in some other case, like in the case of transthyretin, that is a tetrametric protein, if you apply pressure, you dissociate the tetramer. Once you release the pressure, you get back the tetramer. I won't show the data, but that tetramer is a little bit distorted. I mean, it's a tetramer. If you do a gel filtration column, it's a tetramer. But if you change a little bit the condition, you find that it aggregates much faster. So apparently and that's pretty much in the way that Daniel said, that if you get like a seed, in this case the seed might be the tetrameric form of the protein. We also use the expression of Gregory Weber with some kind of conformational drift. It's a little bit of drift conformation. We found that the interaction among the monomers and the tetramer was much weaker. So that